In this video, we'll consider the general structure and properties of two other functional groups, alcohols and ethers. Our learning goals include contrasting oxygen with nitrogen, especially as it functions as a nucleophile. And then we'll also want to identify both the alcohol and ether functional groups and find out what is special about them and how they behave chemically. So what are some similarities between nitrogen and oxygen? Well, they both have non-bonding pairs of electrons, so they have these lone pairs that can then act in a nucleophilic fashion. As a result, they both have hydrogen donor and acceptor properties, so they can both act as either a donor or an acceptor. In the case of nitrogen, it more often acts as an H plus acceptor, and with oxygen, it's kind of variable. It can do both an acceptor and a donor. They both have very strong intermolecular forces. They have some versatility in carbon framework molecules in the sense that they can substitute for both. They can both substitute for hydrogen as in OH or in NH2 at a terminal position, but they can also substitute for carbon as part of the hydrocarbon chain, so they can link two different carbon segments and therefore be part of the chain. Some ways that they're different, they have different bonding capacities. Oxygen has a bonding capacity of 2 and nitrogen of 3. They also have different electronegativities. Oxygen is a bit more electronegative than nitrogen, so when the two are bonded together, oxygen is the one that will draw more electrons. It also creates more polar bonds with carbon as a result of this. They both can be nucleophiles, but amines tend to be stronger nucleophiles than alcohols, which are the OH group. On the other hand, as proton donors, alcohols tend to be better proton donors than amines, but neither one of them is particularly good at donating protons. We begin by discussing alcohols and a related type of compound called thiols. Alcohols basically substitute OH for H in a hydrocarbon, so it's a simple substitution. We would simply take off a hydrogen and replace it with an oxygen attached to a hydrogen. These have a name that ends in the suffix OL, so thus we have things like ethanol and propanol as names for alcohols. There's a related type of compound in which sulfur is used in place of oxygen. In this case, we call these thiols, and again, they simply substitute for a hydrogen and a hydrocarbon. And their names would be, something like ethane thiol, for example, would be an example. We have different types of alcohols, just as we had different types of amines. A primary alcohol is one that would be attached to a carbon at the end of a hydrocarbon chain. A secondary alcohol would be attached to a carbon in the middle of a hydrocarbon chain, but that carbon should also be attached to a hydrogen. Finally, we could have an oxygen attached to a carbon in the middle of a hydrocarbon chain that also is attached to a third alkyl group. In this case, we would have a tertiary alcohol. We have similar sorts of variations for thiols. One of the things that is interesting about oxygen and sulfur is that they don't form particularly strong bonds to themselves. Oxygen's bond, in fact, is 146 kilojoules per mole, which is remarkably weak for an element in the second row of the periodic table. Both of them form fairly sturdy, durable bonds to carbon, so they're more likely to be seen in compounds that involve carbon than they are to be seen in any kind of long chains with themselves. They just can't support that sort of structure. Let's look at some electrostatic profiles for these compounds. We're going to look at a few alcohols, ethanol, cyclohexanol, and a really large one, cholesterol, right? That is also an alcohol. Now, what I want you to see in these MEP surfaces is this signature electron charge distribution in these molecules as indicated in these surfaces. And you'll notice that all of them have this distinctive piece here that is the alcohol group that contains sort of a head that is red and a beak that is blue. And you can see it here in cyclohexanol and also in cholesterol. All right, you will see this sort of signature pattern in the MEP surfaces of all alcohols, and so it helps you identify from the MEP surface that the compound is an alcohol. There is something similar in thiols, except that the sulfur is much larger than the oxygen, so that signature group is like a bigger head with the same sort of blue beak. Also, because sulfur is less electronegative than oxygen, there's less charge separation, so the beak is not quite as blue in thiols as it is in alcohols. It's a subtle difference, but hopefully it's one that you can begin to recognize when you look at these compounds. Let's look at another functional group that involves oxygen, and this is the ethers. In this case, however, oxygen is going to substitute for carbon in a hydrocarbon chain. So in an alcohol, it's basically a terminal group. It's attached on the periphery of the molecule. In this case, the oxygen is in the middle of the chain. It connects two different carbon groups together, so it is branching that. Okay, it can be a linear chain or it can be a cyclic molecule, as we've shown here. We also have polarity in these groups. Remember, oxygen is more electronegative than carbon, so the carbon-oxygen bond is very polar. This puts charge, partial negative charge density on the chain itself, which is different from what we have in a normal hydrocarbon molecule where it's fairly non-polar. Once you have a charge center on the chain itself, that means it can now participate more directly in chemical reactions. Most ethers have dipole moments because of this charge separation, and they can serve as bases because that oxygen does serve a little bit as a nucleophile in the same way that nitrogen does. It's not as strong a nucleophile as nitrogen, but nevertheless, ethers do participate as bases in certain reactions. Ethers have been used for a number of things historically. I'd say the most famous use is diethyl ether as an anesthetic. Now, we don't use it typically in surgical settings because it's very flammable and you wouldn't really want to catch fire while somebody is operating on you. Another purpose that we use ethers for is to bind small positive ions. So this crown ether, 18 crown 6 that's shown here, is a very interesting molecule. And I show the MEP surface here so you can see that the cavity in the crown ether actually is a partial negative charge center. It is very attractive to positive ions. So they will go embed in there because now they're attracted by the electrostatic forces go in there. So it's used especially in synthesis in chemical labs, and this hole in the 18 crown ether is particularly accommodating for certain metals. I should mention too that some antibiotics are also polyethers, more than one ether. All right, as an activity to close this, I want you to take a look at this MEP surface and determine whether it's an alcohol or an ether. I'll give you a moment to think about that. You can pause the video and then I'll come back with the answer. All right, what do you think? Is this an ether or is it an alcohol? Do you see the signature that is typical of alcohols? Well, I don't, so I would assume that this is an ether of some kind. And in fact, when we look at the molecule itself, it is a diether that is cyclic. Looks something like this.